You are being deceived by science, and you don't even know it. Not by fraud, not by conspiracy, but by something far more subtle and far more dangerous. Every time a discovery is announced, a new particle, a signal from deep space, you are not seeing reality, you are seeing a construction, a carefully crafted interpretation filtered through layers of algorithms, models, and human decisions. Between the actual event and the headline, there is an ocean of manipulation, and almost no one can see it. The scientific community doesn't call it manipulation, they call it processing, calibration, noise reduction. But the effect is the same. What reaches you is not what happened. What if the most famous discoveries of modern physics were never actually observed? What if the evidence was manufactured by the very tools designed to find it? What if you've been trusting an illusion? Today, in the final episode of our epistemology series, we are going to show you exactly how this happens and why it matters more than you think. Welcome back to the channel. Today we close a cycle of 11 episodes, and we close with the most fundamental question of all. What does it actually mean to observe something in physics? In previous episodes, we established that physics divides into three epistemically autonomous perspectives: observational data, relations between data, and interpretation. This division is the foundation of our entire analysis, and today we are going to examine the most fundamental of these perspectives, the one upon which all others depend, the data itself. Because here's the uncomfortable truth. The data that reaches us, published, celebrated, taught as fact, is not raw data. It is deeply interpreted data, filtered through layers of algorithms, theoretical models, and human decisions. And in 21st century frontier physics, the distance between raw data and interpreted data is colossal. This distinction, frequently neglected or dismissed as trivial, is the key to understanding the limits of contemporary physical knowledge. And the most dramatic example of this is LIGO, the billion-dollar gravitational wave observatory that in 2016 announced one of the most celebrated discoveries in scientific history. But before you trust that discovery, you need to understand what actually happened. Before we dive in, let me introduce you to the star of this story. LIGO, the Laser Interferometer Gravitational Wave Observatory, is not just one machine. It's actually two enormous facilities, one in Hanford, Washington, and another in Livingston, Louisiana, nearly 3,000 kilometers apart. Each facility is essentially a giant L-shaped ruler, two arms, each 4 kilometers long, containing some of the most perfect vacuum ever created on Earth. A laser beam is split and sent down both arms, bounces off mirrors at the ends, and returns to recombine. The idea is elegant. If a gravitational wave passes through the Earth, it should stretch space itself, making one arm slightly longer and the other slightly shorter. The laser beams, now out of sync, would reveal this distortion as a tiny flicker of light. And when I say tiny, I mean tiny. LIGO was designed to detect changes in length of about 10 to the power of minus 18 meters, 1,000th of the diameter of a proton. That's like measuring the distance to the nearest star with the precision of a human hair. It took over 40 years of development, more than $1.1 billion, and the efforts of over 1,000 scientists. And in September 2015, they announced they had found what they were looking for. But what exactly did they find? And how much of what they found was real and how much was interpretation? Because those are two very different things. And that's what we're about to uncover. So, before we can understand what LIGO actually found, we need to understand a fundamental distinction that most people, including many scientists, never think about: the difference between raw data and interpreted data. In the classical conception of science, raw data is direct observation without significant theoretical mediation. Galileo observes Jupiter's moons. Tycho Brahe records planetary positions. Faraday watches magnetic needles deflect. Of course, even these observations involve instruments, but the mediation is minimal, comprehensible, and crucially verifiable by others. Now, let's follow the journey of a single datum at LIGO, a single piece of information, from the moment it enters the detector to the moment it appears in a published paper. Individual photons strike photodetectors. Electrical signals are amplified and digitized at 16,384 samples per second. Calibration algorithms convert electrical signals into displacement measurements. Digital filters remove seismic and thermal noise. Subtraction algorithms eliminate identified glitches. Matched filtering compares the data with thousands of theoretical templates. And only then, statistical analysis calculates the probability that the signal is real. Each stage depends on theoretical suppositions. The raw datum, the sequence of photons that struck the detector, is inaccessible to the public, and, frequently, inaccessible even to the researchers themselves. But here's the problem no one mentions when they celebrate this discovery. The gravitational wave they were looking for didn't travel through empty space. It journeyed for billions of years across a universe filled with other events, other gravitational waves, massive objects, cosmic phenomena. Each encounter leaves a mark, each interaction modifies the signal. What reaches Earth is not the pristine wave from the original event. It's a signal that has been convolved with the entire history of the cosmos, modified, contaminated, and altered by forces and events we can only partially account for. And then, on top of that cosmic contamination, the signal arrives here, where it encounters a second layer of contamination: seismic activity, ocean waves, track traffic, thermal fluctuations, quantum noise. So here's the uncomfortable question. How do you separate a signal that has been altered by billions of years of cosmic interference from the local noise of Earth, when you've never actually seen the original signal in its pure form? The answer is, you can't, not directly. What you can do is build models, apply filters, and make assumptions. And that's exactly what LIGO did. And this brings us to the heart of the problem. How did they actually distinguish signal from noise? The answer reveals a circularity that most people never see. Here's the central problem. During LIGO's first observation campaign, in 4 months of operation, the detector recorded approximately 100,000 glitches, transient noise events that look extraordinarily like astrophysical signals. Out of those 100,000 events, only 3 were classified as genuine gravitational waves. That means 99.997% of the recorded events were classified as noise. The crucial question is, how did the collaboration distinguish the 3 real events from the 100,000 glitches? The official answer: through templates based on numerical simulations of general relativity. The collaboration holds a bank of hundreds of thousands of theoretical waveforms, representing how the signature of different configurations of coalescing black holes should appear. But here lies the central epistemological problem. The signal was identified only because it corresponded to a pre-existing theoretical model. Any event that did not correspond to a predicted template, however real it might be, would have been automatically discarded as a glitch. This creates an epistemic circularity. We know how gravitational waves should look according to general relativity. We program the detector and the algorithms to filter out everything that doesn't look like this. And when we find something that does, we celebrate the confirmation of general relativity. What was never tested? The possibility that real gravitational waves reach us in forms different from those predicted, or that unknown astrophysical phenomena exist that produce signals similar to the templates. The experiment was designed to find what the theory predicted, and surprise, it found exactly that. There's an even more fundamental critique here. In a dataset as vast and noisy as LIGO's, it is statistically expected that some random patterns will resemble the search templates, regardless of whether they correspond to real gravitational waves. With approximately 100,000 glitches recorded in 4 months, the search space is large enough for spurious correspondences to occur. The confirmation of a template is, therefore, not evidence that the postulated phenomenon exists. It is evidence that the search method worked as designed. Any set of templates based on any theory would have a non-negligible probability of finding something in the noise, provided the templates were sufficiently numerous or flexible. And here we formulate postulate 25 of our series, the malleability of template confirmation. Postulate 25, the malleability of template confirmation. In a sufficiently vast and noisy dataset, any set of theoretical templates, provided they are sufficiently numerous or flexible, will find patterns that confirm the existence of the postulated phenomenon. Template confirmation is, therefore, epistemically weak. It demonstrates that the search method was able to find what it was programmed to look for, not that the corresponding phenomenon exists in nature. In other words, if you design a machine to find unicorns and you give it 1 billion data points, eventually it will find a pattern that looks like a unicorn. That's not discovery. That's confirmation bias built into the machinery. But there is a mechanism protecting these discoveries from critical scrutiny: spectacle. The announcement of the Higgs boson in 2012, complete with tears, applause, and global media coverage, is a paradigmatic example. The same applies to the gravitational wave announcement by LIGO, presented as the inauguration of a new era in astronomy. Contemporary scientific communication frequently replaces logical persuasion with aesthetic seduction, forming fans instead of understanders. Studies on narrative power in science communication confirm that well-told stories increase message retention and acceptance, but they frequently do so despite the fragility of the logical arguments, not because of them. Narrative transportation, emotional immersion in the story, suppresses critical analysis and makes the listener more susceptible to beliefs they could not rationally justify. The consequence for the cases we've discussed is direct. When an epistemically fragile discovery is announced as a spectacular triumph, a social climate is created in which questioning the interpretive basis of the discovery is seen not as an act of scientific rigor, but as an aggression against science. And so we formulate postulate 27, the aesthetic shielding of big science. Postulate 27, the aesthetic shielding of big science. The spectacularized dissemination of big science discoveries, by replacing logical persuasion with aesthetic seduction, creates a social shield that discourages critical scrutiny. The more beautiful and celebrated the narrative of the discovery, the more costly it is to question its epistemic basis. And here's the most disturbing part. LIGO is not an exception, it's the rule. At the Large Hadron Collider, proton collisions occur at a rate of approximately 40 million events per second. The electronic trigger system discards more than 99.99% of events before they are even recorded. The epistemological problem. The trigger system is programmed to select events that look like what physicists expect to find. If a completely new and unexpected phenomenon occurred, it would probably be discarded as uninteresting by the trigger. The circularity is the same. We program the detector to look for what we expect. We find what we expected. We celebrate the confirmation of our expectations. At IceCube, which searches for ultra-high energy astrophysical neutrinos, researchers depend on complex models of atmospheric flux and on selection algorithms based on Monte Carlo simulations. The circularity, the background models, are based on previous measurements that depended on assumptions about what was signal and what was background. The James Webb Space Telescope produces raw images that are transformed into scientific images through dozens of processing stages: detector calibration, dark current subtraction, flat field correction, cosmic ray removal, alignment of multiple exposures. The final result, the dazzling image we see in the news, is deeply interpreted. Where does raw data end and interpretation begin? The answer, in practice, is nowhere. There is no clear line. The most paradigmatic example of this circularity at the LHC is not the trigger process, but the very nature of the announced discovery. The discovery of the Higgs boson in 2012 acutely illustrates the problem of the indistinction between raw data and interpreted data. What was observed was not a particle in the classical or even usual quantum sense. What was detected was a statistical resonance, an excess of events around a mass of 125 giga-electron volts in the ATLAS and CMS detectors. This resonance is interpreted as the manifestation of an excitation of the Higgs field, but this interpretation rests on a highly abstract and to a certain extent circular definition. The particle is defined as a localized fluctuation of a field, and the field in turn is inferred from the existence of the particle. Moreover, it was never directly proven that the observed resonance is a boson, that is, that it possesses integer spin and Bose-Einstein statistics. These properties are attributed by assumption based on consistency with the standard model. Therefore, the statement "we discovered the Higgs boson" hides a series of inferential leaps, from statistical signal to resonance, from resonance to particle, from particle to boson, and from boson to Higgs field. Each of these steps is theoretically loaded and not free from controversy. And here's the connection to our central theme. The discovery of the Higgs boson is not an observation, it is an interpretation built on layers of processing, selection, and theoretical assumption. The raw data, the actual collisions, were discarded at a rate of 99.99%. What remained was a statistical pattern that could only be seen through the lens of the standard model. LIGO cost over $1.1 billion. The LHC cost $13 billion. James Webb cost $10.8 billion. When this level of investment is at stake, the institutional pressure to produce positive results is overwhelming. The LIGO collaboration includes more than 1,200 scientists from over 100 institutions. The ATLAS collaboration includes more than 3,000 physicists. These scientists depend on the experiments for their careers, salaries, prestige, and future funding. In previous episodes, we identified the Babel effect, the universal process by which organizations deviate from their formal objectives, and it operates here with clarity. Internal competition. Within each collaboration, groups compete for authorship, access to data, and leadership positions. Questioning the purity of data threatens the legitimacy of the organization. Inter-organizational competition. Collaborations compete for funding and prestige. Admitting that data is interpreted would weaken the claim of discovery. And combat against non-adherence. LIGO's critics, Creswell, Jackson, Naselski, faced difficulty publishing, were publicly disqualified, and saw their careers threatened. The medieval heretic was burned at the stake. The modern heretic is burned professionally. The function is the same, to signal that divergence has prohibitive costs. But why do intelligent, well-intentioned, honest scientists not perceive the problem? The answer is what we called in a previous episode the observer's lens, the interpretive filter conditioned by theoretical commitments, community consensus, and institutional pressures that shapes scientific perception even before any conscious evaluation. The physicist trained within general relativity, who built their career on it, who publishes in journals that presuppose it and attends conferences that celebrate it, is not in a position to see LIGO's epistemic circularity. The circularity is invisible because the lens makes it invisible. And there is a mechanism of homogenization of scientific perception. Scientific communities, by defending consensus, systematically produce researchers who share the same lenses, paradigms, and dogmas. The process operates through the educational pipeline, Students are trained to see the world through their predecessors' lenses. The selection filter, those who question too much are filtered out, and the invisibility of the lens, when everyone shares the same assumptions, they cease to seem like assumptions and begin to seem like reality. And that's why the solution cannot come from within the system alone. It requires external mechanisms, explicit labeling, meta-theoretical suspension, and a public that understands the difference between what was observed and what was inferred. So, what's the solution? If we cannot eliminate interpretation from data, what can we do? The answer is twofold. First, explicit epistemic labeling, and second, periodic meta-theoretical suspension. In LIGO's case, a typical label would read: the analyzed signals were extracted from the Hanford and Livingston detectors through matched filtering with templates based on numerical simulations of general relativity. The classification as a gravitational wave depends on the validity of these templates and on the assumption that residual noise is Gaussian and stationary. The detection is, therefore, labeled as observation of foundations dependent on the interpretation given by general relativity. This label does not diminish the technical feat. It simply declares the conditions of knowledge production, allowing readers, funders, and other scientists to evaluate the degree of uncertainty involved. But labeling alone is not enough. It makes contamination visible, but to question it, we need meta-theoretical suspension, the practice of temporarily examining scientific questions without the filters of current models. It is analogous to Husserl's phenomenological epoché, the temporary suspension of the assumptions that normally guide perception in order to examine these very assumptions. Asking, what exactly am I accepting when I accept this datum? What interpretations am I bringing to this observation? How would the data look if I suspended my current interpretive framework? These are the right questions to ask, but asking them leads us to a deeper realization, one that might feel uncomfortable at first. Now, at this point, you might be thinking, okay, so if interpretation is unavoidable and raw data is inaccessible, what's the point? Are we just supposed to give up on science? No, and that's where the most important insight of this entire series comes in. Here's the trap that many people fall into when they encounter this problem. They think the only solution is to eliminate interpretation entirely. Build neutral detectors, create objective algorithms, develop theory-free protocols. But that elimination is impossible. Every measuring instrument incorporates theoretical presuppositions in its design. Every filtering algorithm depends on human decisions about what's relevant. Every statistical analysis starts from prior models of what's expected. So, if we can't eliminate the problem, what can we do? The answer is what we call epistemic awareness, and it's more powerful than you might think. Postulate 23, the pragmatic solution of problems. We formulated this as Postulate 23, the pragmatic solution of problems. Frequently, the consideration and awareness of a problem produce more epistemic benefit than premature or impossible attempts at solution. This does not imply renouncing the solution when it is possible. It implies recognizing that in cases where the solution is impossible or beyond the practical horizon, awareness is the most practical and viable intervention available. In other words, pretending the problem doesn't exist is the worst option. The elimination of interpretation from data is frequently impossible, but awareness of that interpretation is not only possible. In most cases, it is the most practical and viable path we have.
And this awareness translates into concrete practices. Recognition of a denial. Pretending data is pure when it isn't leads to conclusions the data cannot support. Transparency over opacity. Declaring which processing stages were applied transforms interpreted data from a black box into a traceable object. Provisionality over certainty. Treating each discovery as a well-founded interpretive hypothesis allows science to advance without becoming dogmatic. Humility over arrogance. Recognizing that our interpretations may be wrong is an epistemic virtue that protects against dogmatism. And here's the crucial point. This awareness doesn't weaken science, it strengthens it. Because a science that acknowledges its limitations is more trustworthy than one that hides them. A scientific community that declares its assumptions is more rigorous than one that naturalizes them. And a public that understands the interpretive nature of data is less vulnerable to manipulation. We cannot eliminate interpretation from data, but we can stop pretending it isn't there. And that awareness changes everything.
This episode concludes our series on the epistemology of physics, and the conclusions are clear. First, pure raw data is a generally inaccessible abstraction in contemporary frontier physics. What reaches us is almost always interpreted data. Second, this interpretive contamination is neither recognized nor corrected because the organizations that produce the data are the same ones that interpret them, announce them, and benefit from them. Third, the uncritical acceptance of interpreted data as raw is a collective dogma formed by sedimentation, protected by secularized suppression mechanisms, and maintained by the fusion between big science, state, and capital. And here is what makes this so dangerous. This contamination doesn't stay contained, it propagates. Every theory built on top of this interpreted data inherits the contamination. Every experiment that uses these confirmed discoveries as its foundation is standing on sand. The entire edifice of modern physics, from gravitational wave astronomy to the standard model of cosmology, is built upon a base that was never as solid as we were led to believe. When the foundation is contaminated, everything built upon it is compromised. And the higher the structure grows, the more invisible that original contamination becomes. Fourth, eliminating the problem may be impossible. But awareness of the problem is not only possible, it is necessary. Fifth, explicit epistemic labeling offers a concrete mechanism to restore the integrity of the empirical base. And sixth, interpretive contamination is invisible to those who produce it, not through dishonesty, but through cognitive conditioning. Periodic meta-theoretical suspension is the only known antidote. The illusion of interpreted data is not only an internal problem of physics, it is also a problem of public communication. When big science announces interpreted discoveries as if they were direct observations, and does so through an aesthetic apparatus that discourages scrutiny, it is not only deceiving itself, it is deceiving the society that funds it. This video is the last of our journey of 11 through the foundations of epistemology of physics. But this is not a story of pessimism, it is a story of preparation. By exposing the illusion of interpreted data, we have done something remarkable. We have reopened doors that had been sealed against reinterpretation. With this complete epistemological review, data, relations and interpretations, individual and collective dogmas, the Babel effect, demarcation criteria and awareness of suppression mechanisms, we are ready for something greater. We are ready for a fundamental reinterpretation of physics. Keep following the sequence in the exact order, because in video 12 we will start proposing a new alternative. Subscribe so you don't miss the turning point, and until the next path. What you've just seen is part of a much larger project, one I've been developing independently for over 40 years. It's a complete framework and it's fully laid out in my forthcoming book, which you can find linked in the description below. Everything in this video, from the core ideas to the script, is original content created by me. The avatar that appears in this video is my digital clone, which mimics my voice and appearance and is used to produce a better result with the available resources. Starting next episode, we stop deconstructing. We start rebuilding. We will propose a new understanding of physical nature, one that does not hide behind the illusion of interpreted data, one that acknowledges its foundations honestly, and one that builds on ground we have cleared ourselves. The epistemological review was not an end in itself, it was the necessary preparation for what is to come. Thank you for joining this journey,
And get ready, because what comes next will change how you see everything. If you enjoyed this deep dive, please give it a like and subscribe for more explorations of science, philosophy, and the structures that shape our thinking. The full paper is linked in the description, along with my website and the rest of the series.